Hi, Jeff here again, and welcome back to the DIVA 4.0 tutorial series. Today we'll continue with ArchSim and we'll take a look at multi-zone modeling. So in previous tutorials, we were running our energy simulations on single thermal zones. Now in many cases, a single zone might not be sufficient to fully understand the thermal performance of a large space or a building. And that's because it doesn't fully take into account the effects of the perimeter zones. So there might be solar gains, envelope heat gains and losses, localized temperature effects that might be happening at the perimeter that might be different on certain sides of the building at certain times of the day compared to others. If we just had a single zone, we would sort of wash down that localized effect. And that's why it's important to divide a building up into different zones in order to understand how the performance of different orientations, as well as different building uses, has an effect on the overall performance of the building. So here we have a simple multi-zone model set up in Rhino. We have 5 different zones. 4 of those zones are on the perimeter, on the zone perimeter layer, and they are about 48 meters long each by 10 meters deep and 3.5 meters high. And we have 1 zone in the core, on the core layer. Now this model is loosely based on the example office that we used for our DIVA tutorials. And they also have windows that you can see here on the windows layer. Each window is about 50% of the wall area that hosts them, and they are coincident with these exterior walls on the perimeter zone. So the first thing that we'll want to do to set up our multi-zone model is to assign the multiple thermal zones to the thermal zone component in ArchSim. In our previous tutorials, we were using the brep component to assign our shoebox geometry as a single zone for the ArchSim component, for the thermal zone component. Now we can use a similar process where instead of setting 1 zone, we can set multiple zones to this brep input, and let's just demonstrate that right now. So by right-clicking on this component, I can say set multiple breps, and in Rhino, I'll go ahead and just select all 5 zones by dragging my cursor. Now when I select these zones, you can see that some text tags have popped up in our Rhino viewport. And these correspond with the name that I had input for the thermal zone component in our previous tutorial. I called it example zone. And these names are appearing because I have the model output in the zone connectivity network into the model input of the surface analysis component that we set up in our previous tutorial. Having the preview turned on in this component will tag the multiple zones in our Rhino viewport. And it gives us a numeric suffix to each zone, depending on the order that that zone appears in the list of inputs. So for example, our eastern perimeter zone is the first in the list, and it's called example zone 0. The core is the second in the list, and so on. Now this might be fine if all of the uses in terms of the internal gains, the characteristics of the building envelope, and the conditioning properties for all of the zones were the same. We can keep them all in this one geometry input and use only 1 thermal zone component for our model. But in this case, we have some perimeter zones which would be considered open office areas as a typical floor in an office building. And we have a core zone, which would be where the circulation and other support spaces would be located. They're going to be performing differently. They'll have different programs. So it's probably a good idea to include a second thermal zone component into our ArchSim setup. So I'll go ahead and make a copy of all of these components, the brep input, the name, and the thermal zone component. I'll make this first one the perimeter, so I will change the name of the tag of the panel to perimeter. And I'll make the second zone core. I'll go ahead and select only the perimeter geometry for my perimeter zone component. And you can see that they're tagged accordingly. And then I will also right-click here and select that 1 core object. Now the name doesn't appear because it's not yet plugged into the zone connectivity network. So I'll go ahead and connect it into the zone connectivity network, but I'll hold down Shift as I do that so that multiple data streams can go into that 1 single zone input. After I do that, you can see that the perimeter zones now have the perimeter tag on them, and the core zone has the core tag. Now that we've properly assigned the geometry to the thermal zone components, let's go check the settings to make sure that the settings match the way that we want to set up the perimeter zone characteristics and the core. So first I'll start with the perimeter. We'll keep the perimeter settings the same as how we had before. So we'll leave the people density the same way that it is. The equipment and lighting, power densities, and schedules will leave the same. For the conditioning, we want to make sure that we have heating and cooling turned on. We had them turned off for our previous tutorial, but we'll go ahead and leave the default schedules on for now. Ventilation will leave the same. We have some infiltration in this zone. And for the constructions, we can leave some of these defaults. However, now the partitions will be coming into play because the demising surfaces between zones will be partitions. So we'll go ahead and set a construction for this. I will make this partition material construction for our partition. And I'll select OK just for the moment so I can zoom out, and using the surface analysis tool, I'll just indicate what those partitions actually are. So you see that after plugging in the partition output into the BREP component, the highlighted surfaces are those surfaces that are dividing thermal zones from thermal zones, as opposed to the surfaces that divide the zones from the exterior. So this happens when we have more than one zone in our model, and the partition is only the sort of interior surface, or a shared surface, a shared wall between two thermal zones. And now going back to the thermal zone settings for our perimeter zone, I want to make sure that in the constructions tab that we have the material that we want assigned for this partition. And I'm just selecting this partition because it happens to be a low mass kind of thin construction partition. We won't have any slabs in our model because we have no thermal zones to the top of the zones that we're testing. So slabs won't be coming into play for this tutorial. I'll leave the ground the same, and I'll leave the facade the same for today. And I'll press OK. Now for the core zone settings, I'll go ahead and make adjustments to the thermal zone settings for the core zone. So let's just say that our core is mainly support spaces, corridor, circulation, mechanical, and things like that. So there are no people in this space. So I'll go ahead and turn off the people. And as far as equipment, I can just say for the purposes of this tutorial, there aren't any computers or things like that in this zone. So I'll turn that off as well. There will be lights, and I'll go ahead and leave the lights on for this tutorial. As far as conditioning is concerned, I do want to have heating and cooling on for both of these. For this core zone. And for infiltration, I'll go ahead and leave this the same. The infiltration might be different. There won't be any doors to the exterior in this core zone, so it's likely that the air exchange to the exterior is a little bit different, but I'll just go ahead and leave it the same for now. And then for constructions, I want to be consistent with my construction, so we're going to use the same roof. I want to use the same partition because this particular zone shares walls with the perimeter zones, which we just modified. So I want to make sure that it has the same partition type so that we don't cause any errors. It was this partition type here. And I'll go ahead and leave the rest of these material constructions the same. Next, for windows, we need to assign these windows to the window thermal zone component. So I'll go ahead and set multiple BREPs. And I'll utilize the Rhino layer to make selection easier. So I'll say select objects. In my window settings, I will keep the same settings that we had before. And if I go back to my surface analysis tool, we can plug in the different output components into the BREP container to just make sure that we've modeled this correctly. So by plugging in facade into the BREP, we see that only those exterior walls are being now previewed in our Rhino viewport, and that's correct. If we were to see some interior walls highlighted in red when we plug in the facade into the BREP component, we would know that we have some kind of modeling error or something was wrong in the setup of our zone geometry, and we could take a look at it to make sure that everything was modeled correctly and that all of the inputs in our zone connectivity network were set up correctly. Plugging in the partition once again shows us that these interior shared walls are our partitions, which is good. We won't have any ceiling because we don't have any stacked zones, although we do have a roof and we do have an external floor. Just as we didn't have any ceiling, we won't have any floor, which is the sort of shared floor between two thermal zones. And we would expect to have our windows highlighted, and that's correct. Great, now that we've checked our setup and we've already adjusted our thermal zone and window settings, we can now make some adjustments to the Energy Plus component to prepare for the energy simulation. And we'll go ahead and give this energy model a name. So I'll call it MultiZone. Next, we want to give the proper directory to save our input and output files, and I'll create a subfolder in the ArchSim results folder called MultiZone. We'll just double check that we have the right EPW file selected, and it's the Boston Logan Airport. That's correct. And let's click on our settings to make sure that we have the correct run period, resolution, and outputs for our simulation. So the run period, let's go ahead and do an annual simulation just for this demonstration from January 1st to December 31st. The resolution will be monthly. And for our output variables, I'll clear out the selections. Let's go take a look at lights. So we'll click the zone lights electric energy. This will look at the lighting energy consumed. And then let's go take a look at the zone ideal loads, total heating and total cooling energy. Zone ideal loads, total cooling energy here. And we'll press OK. Great, now our Energy Plus component is set up, and I will run the simulation. Now, as we did with the previous tutorials, when the simulation is complete, we can access the data using the ArchSim components, as well as looking at the CSV output file directly by navigating to it in Windows Explorer and opening it up in Microsoft Excel. I'll go ahead and navigate to the MultiZone subfolder that we created, and I'll open up the MultiZone CSV file to look at the data directly in Excel. Now, when I open up this file, you see that we have quite a bit of data. We have a lot of columns of data here in this Excel file. And as with the previous tutorial, the first column is the date and time. And I will make this a little bit bigger so that we can visualize the titles more clearly. I'll expand this. Now, the first set of zones are the lights electric energy for the different zones. You see that there's a column for any given output. There is a column for each zone that is in our energy model. So we have these 4 perimeter zones, and we have a core zone, and this is for the lights. And next we have zone ideal heating and cooling for the individual zones, and it's a little bit hard to read because of the size of the cell and the length of these titles. But if we expand this a little bit, you see that we have for perimeter zone 0, we have the total heating and then cooling. And then perimeter zone 1, we have the heating and cooling and so forth. Now, we can visualize this data individually. We can look at single zones within this data set and visualize them as graphs using Excel. But if we want to create a total energy or a total heating and cooling plot, for example, we can isolate or rearrange some of these columns and order them in a way that lets us look at the total loads for the building. So we can leave the lights here because they're in order, but here we have heating and cooling for these zones. We have for any given zone heating and cooling, and then the next zone heating and cooling afterwards. So I'll go ahead and rearrange these by inserting a column or a row up above, and I'll just quickly give each one a little tag so that I can rearrange them using the sort and filter tool. There's many other ways to do this, but this might be one sort of simple way to do it. So heating and cooling, and I'll go ahead and copy the heating and cooling. I want an H for every heating column and a C for every cooling column. I'll go ahead and drag this over so that the H always corresponds with the heating column and then the C with the cooling. Now I'll select these columns and I'll use the sort and filter tool to select custom sort. And I will change the options to sort from left to right. I want to sort these alphabetically from left to right. I want to sort them alphabetically according to that first row, and sort on the values from A to Z, and I'll press OK. So now I have the cooling loads first, all of the cooling loads, and then all of the heating loads. So now I can create a new column that's the total cooling. and total heating. I can make a total lighting column here. And for the total cooling, I'll just go ahead and sum up all of these rows that contain the C. And then for the total heating, I'll sum up all the rows that contain the H. And for the total lighting, I'll go in and highlight only those rows that contain the lights. I'll make these bold, and I will drag this formula, so it's going to be summing these up accordingly. To the same formula for this row, if I drag this down to the subsequent rows, it will copy those formulas. And I will select these columns, and holding down Control, I'll also select the date and time. So you can see I have the date and time selected, and then my total values here selected. And I'll go ahead and insert a line graph. So if I zoom in, I can make this a little bit bigger. You can see now I have a line graph for my multi-zone model. It corresponds to the total cooling for all of the zones combined, the total heating, and the total lighting. Now this gives us a picture of the entire building, the whole building, in terms of the ideal loads for total heating and cooling, and then the lighting energy. But it doesn't really give us a sense unless we wanted to go in and graph individual zone performances and compare them to others. If we were to graph all of this, it would be a harder to read line graph. So what we can do is actually use the ArchSim interface to give us a relative sense of how the zones are performing relative to one another in terms of these metrics, so cooling, heating, and lighting. So I'll switch back to ArchSim, and we can use the model output to start this workflow to map the results back into the Rhino model, so we can see some color mapping, some false color mapping of the different metrics onto the thermal zones. So to do that, I will use this load zone results component. I'll plug the model output into the model input, and I'll put a Boolean toggle on the canvas, and I'll set it to true. This will activate this component, and it's previewing, it's showing that these zones are being recognized, but I'll turn the preview off for the moment. Now under outputs, we can select which metric we want to see. So I'll go ahead and let's just start with lights for now. I'll select that, and I want to keep normalized by floor area clicked. This is important because it's going to be for whatever metric that we are seeing for the outputs. So if it's lights, electric energy, and joules, it will divide the total light energy for any given zone by the floor area of that zone. And so in other words, it gives us the lighting energy intensity of a given zone. This way we can compare zones of different sizes in a way that's apples to apples. Next, let's take a look at this results output. I will put a panel on the canvas, and I'll plug the results output into this panel. And you see that we have a tree of multiple branches. Each branch is a list of 12 values, one for each month. And there are the same number of branches as there are zones. So you can see that there are 5 branches, starting with the number 0, going down to the number 4. So there's 5 branches, and this means there's a data set of monthly lighting energy intensities for each zone. Now I want to map, let's just say I want to map the total annual lighting energy intensity back onto the zones. I'll need to sum these monthly values up. So I'll put a mass addition component onto the canvas, plug the results into that, and then take a look at those numbers. So now we have a branch with we have a tree with 5 branches, except now instead of each branch being a list, we have each branch being just the total summed annual value for this lighting energy intensity. But in order to properly input these numbers into a way that we can generate colors mapped onto our geometry, I want this just to be a single list. So I'll go ahead and flatten this data so that there are no longer any branches and it's just a single list. Next, I want to put a gradient component onto the canvas. I want to have something that I could use to change the colors of, or to map the results on a given color gradient back into my Rhino geometry. So I'll put a gradient component here on the canvas. I'll go ahead and change the preset by right-clicking here on the component and going to presets. I'm going to move up a little bit so I can see. And then going to presets, I'm going to select this one right here. And you see this gradient component has a few inputs. It has a lower limit to define what my gradient range will start with, an upper limit to show where the gradient range ends, and then a parameter along the gradient range, so a set of data that I need to plug in for that gradient range. So the range of along the gradient that I want to plug in is these values for total lighting energy. So I'll go ahead and plug that into the T. Next, I want to know what my starting point and what my ending point is. And you can see that this represents a range of values and that there's a low number and a high number. But I want to be able to input those two numbers into this gradient component. So to do that, I'll use the bounds component, which creates a domain based on a given list of numbers. So I'll go ahead and input that. And my domain, if I hover over here, you can see that there is a domain from 3.8 to 3.8 to the 10 to the 7 to 1.7, 10 to the 8th. And I should mention that these numbers are quite high because we're dealing with energy in joules, and they have not been converted to kilowatt hours. And so since we are normalizing, they're joules per meter squared. So now that we have the domain, we can split the domain up into a start point and an end point. And to do that, I'll use the deconstruct domain tool right here. I'll plug in this domain, and now I have a start point, which is the low value in my list, and an end point, which is the high value in my list. And I can simply plug those in to this gradient. Although one thing that I do want to modify about what I just did is, you can see that this is a color scale that runs from red through yellow, then to blue. That means the lower values will be in the red and the higher values will be in blue. I think intuitively we might want to switch that so that the lower values are blue. Instead of modifying these gradient points, which we could do, I'll just go ahead and swap the endpoint and the start point so that the higher number is my start point in the domain and the lower number is the endpoint in the domain. It just basically swaps the order where the gradient is going to be displayed in a way that the gradient is going to be displayed. Great, now to map this color gradient onto the geometry, I'll need to put a custom preview component onto the canvas so that I can apply these colors to a geometry in my model. And the colors will be this shader, the preview shader override. So the colors will be the output of my gradient. And now for the geometry input, the geometry to preview, now I have my colors that are corresponding to these numbers, which is, remember, the total lighting energy density for our simulation. Now I just need a list of geometry that is corresponding to these numbers in the same order to be input into this G. And if we take a look at the zone output of our load zone results component, I'll plug that into this panel that I just copied. You see that I have a list of B-reps in the same order as the results data. I'll just need to flatten this basically as an output so that the list is structured the same way as this list of energy results from my simulation. And now that I have this flattened, I'll go ahead and plug this into the geometry of my preview. And you can see that according to the gradient and the low and high values of my list, it maps different colors onto our Rhino geometry based on the thermal simulation results. So you can see that the core has the highest results. Remember, I swapped this gradient, so the higher numbers are now red and the lower numbers are blue. The core, because it doesn't have any windows and it's not receiving any daylight to dim down the lights in this zone. All of these zones have continuous dimming. It is consuming the highest amount of lighting energy, whereas the perimeter zones are consuming less energy, owing mostly to the dimming that's occurring because of the large areas of windows. And we would expect that the north consumes a little bit more lighting than the other zones because it's only really receiving reflected light because it's facing north. Now we can also change the outputs that we're mapping here onto our geometry by just modifying the output variable in our load zone results component. So by clicking on the outputs again, instead of zone lights energy, I can click on the zone total heating energy. And now you can see the heating energy loads, the total heating energy, being represented in terms of their ideal energy load density, because it's normalized by the meter squared, here mapped onto our zones. Now the south perimeter zone has the lowest heating load because it is receiving a lot of passive solar energy from the sun for most of the year because of its orientation. The north, because it doesn't receive any direct sun, or it doesn't receive much direct sun, it has the fewest amount of solar gains, and it requires the highest amount of heating energy to maintain comfort temperatures. And depending on the output metrics, we can remap, we can display different metrics and different outputs on our geometry and explore the relationships, the relative performance of different zones within our multi-zone model. Great, that about wraps up how to set up a multi-zone model. I hope you will join us for the next tutorial. Thanks a lot.